Welcome to the Explainer. Today, we're really getting into one of the most fundamental challenges in all of statistical modeling. I'm talking about the modeler's dilemma.
So this really is the question that keeps every data scientist up at night, right? We're trying to estimate some true underlying function, we'll call it f, that connects our inputs to our outputs. But here's the catch. Every single data point we see has some random, irreducible error baked into it. The real trick, the art of it all, is figuring out how to capture that true signal, that f, without getting completely fooled by all the random noise that's just part of the data.
All right, so here's our game plan. We're going to kick things off with the bias-variance frontier. Then we'll see how to escape the linear trap and get a handle on model flexibility. From there, we'll dive into a tricky problem called collinearity, look at how shrinkage methods can save the day, and wrap it all up by asking the big question. Are we trying to predict, or are we trying to infer?
All right, let's jump right in. At the absolute core of building a good model, you've got this constant tug-of-war between two different kinds of error, bias and variance.
So this really lays out the whole challenge right in front of us. On one hand, you have these simple, rigid models. They're straightforward, but if reality is more complicated, they're just wrong. That's high bias. We call it underfitting. On the other hand, you've got these super flexible models that can twist and turn to fit anything, but they're so flexible they end up fitting the random noise in your specific training data. That's high variance, or overfitting. The name of the game is finding that perfect sweet spot right in the middle to get the lowest possible error on data you haven't seen yet.
So let's talk about that first problem, high bias. How do we fight it? Well, we need to give our models more freedom, more flexibility, so they can actually capture the messy, non-linear patterns we see in the real world. It's all about breaking out of those rigid, straight-line assumptions.
And here's our toolkit for doing just that. You can start with something like polynomial regression, but honestly, they can get a little wild and unpredictable, especially at the edges of your data. A much more powerful and stable approach is using regression splines. The idea here is brilliant. Instead of one crazy polynomial for everything, you fit simpler, low-degree polynomials in different local regions. You stitch them together smoothly at these things called knots. It's so much more controlled. And then you have GAMs, generalized additive models, which take this even further. They let you model your outcome as a sum of these nice, smooth, flexible functions. It's a fantastic way to get flexibility without sacrificing too much interpretability.
Okay, so we've given our model all this new power, all this flexibility to beat bias. But, as you've probably guessed, that power comes with a huge risk, overfitting. If we're not careful, our super flexible model will just end up memorizing the training data, including all the random noise. And that means it'll have high variance and perform terribly on new data.
And this is absolutely key. You can't, I repeat, cannot use the training error to decide how flexible your model should be. Why? Because the training error will always go down as you add more complexity. It's a trap. So what do? We use something like k-fold cross-validation. This is how we get an honest estimate of how our model will do on unseen data. By testing it on different folds of the data, we can see how different levels of flexibility, say the number of knots in a spline, actually perform in the wild. This lets us find that sweet spot that truly minimizes the test error.
All right, so let's say we've done all that. We've built a flexible model, we've tuned it perfectly with cross-validation. We should be good to go, right? Well, not so fast. There's another sneakier problem that can pop up and absolutely wreck our model stability by jacking up the variance. And that problem is called collinearity.
The best way to think about collinearity is like having two witnesses in a trial who tell the exact same story. When your predictor variables are highly correlated, they're essentially saying the same thing. They contain redundant information. And the model gets confused. It has no idea how to assign credit or blame to each individual variable. This uncertainty makes the coefficient estimates go wild, and their standard errors just explode, making it impossible to tell what's actually important.
So how do we spot this, especially when you have multiple variables all tangled up together? We use a great diagnostic tool called the variance inflation factor, or VIF. It does exactly what its name says. It tells you precisely how much the variance of a specific coefficient is being inflated because of its relationship with the other predictors in the model.
And here's the number to watch out for. As a rule of thumb, if you see a VIF that's higher than 5, and especially if it's over 10, you've got a problem. A VIF of 10 literally means that the variance for that coefficient is 10 times larger than it would be if that predictor were on its own. That's a huge red flag for model instability.
Okay, so let's recap.
We have two big culprits behind high variance. One is just having too much flexibility leading to overfitting, and the other is this nasty collinearity problem. Now, what's really cool is that there's an elegant family of methods that can tackle both of these problems at the same time. These are called shrinkage or regularization methods.
First up is ridge regression. What ridge does is it adds a penalty to the model fitting process. This penalty is based on the sum of the squared values of all the coefficients. Now, what does that actually do? It forces the model to keep the coefficients small. It shrinks them towards zero. This has a fantastic stabilizing effect, especially when you have collinearity, and it dramatically reduces the model's variance. It sort of puts a budget on how big the coefficients can get, but it very rarely forces any of them to be exactly zero.
Then we have the lasso. Now, at first glance, it looks almost the same as ridge, but it uses a penalty on the sum of the absolute values of the coefficients. And that one tiny change from squared to absolute value makes a world of difference. Why? Because the lasso's budget has sharp corners. And what happens is, the optimal solution often lands right on one of those corners, which means some of the coefficients get pushed all the way to exactly zero. So the lasso doesn't just shrink coefficients, it performs automatic variable selection for you. It's an incredibly powerful tool.
So, we've walked through the whole landscape. The bias-variance trade-off, the tools to manage it, the pitfalls like collinearity, and the solutions like shrinkage. But at the end of the day, what actually makes a model the best one? Well, that really comes down to a fundamental question. What is your goal?
It all boils down to this. Are you building a model for prediction or for inference? If your one and only goal is to make the most accurate predictions possible, you might not care how the model works. It can be a total black box. In that case, you'll probably lean towards those more flexible models to squeeze out every last drop of accuracy. But if your goal is inference, if you need to understand the why, to explain the relationships between your variables and the outcome, then interpretability is king. And for that, you might deliberately choose a simpler model, even if it means sacrificing a tiny bit of raw accuracy.
So, the next time you sit down to build a model, this is the question you need to ask yourself first. What matters more here? Getting the right answer with the highest possible accuracy, or deeply understanding why it's the right answer? There's no single best model that fits every situation. The real art of data science is knowing where you need to be on that bias-variance frontier for the job at hand. And that right there is the heart of the modeler's dilemma.